So we've just finished talking about one-to-one functions, and now we want to move into defining what inverse functions are. So the definition for an inverse function is, let's say we have a one-to-one function. So remember, a one-to-one function is a function where for every y value you have exactly one x value. So the inverse function of f, and we're going to call the inverse function of f, we're going to call f with a little superscript -1 here. This thing I'm underlining in red, that's called the inverse of f. F with a -1 is called f inverse. That's defined as follows. F inverse of y equals x precisely when, that double arrow there means precisely when, f of x equals y. So what is that saying exactly? So the idea is you have this function that's one-to-one. So back here we have the domain of f. And our function is like a machine where we're going to take x, right? And we're going to plug that into the machine. And out the other side is going to come something called y. So here we have the range of f. So you plug in x into the machine and you get out y. And that's basically what I'm underlining in blue is saying, right? The forward. So you plug in x and out the other side comes y. Now you have another machine, which we're going to call red, that basically does things in reverse. So I'm going to underline this in red here. The idea is you plug in y into this machine. I'm going to call it f -1, right? F superscript -1, that's f inverse. You plug in y and out the other side comes x. So the blue function f takes x to y, and the red function f inverse takes y back to x. That's all this is saying. Okay, so we want to look at some properties of functions and their inverses. I'll call this properties of inverse functions. Let's call it that, properties of inverse functions. Okay, let's say we take f inverse and compose it with f. F inverse, compose it with f, and plug in x. Now let's think about that for a second. So f inverse is red, f is blue, and x, let's say, is green. So remember how this works with your composition. So on the outside, you have the left function, which is f inverse. And on the inside of that, you're going to have f of x. So basically, we're going to start on the inside here, right, with f of x. So we're starting with x as the input. That gets sent here to y, right? So I'm going to replace f of x with y. And then y, if you follow the arrows, y goes through f inverse and it gets sent back to x. So the property that we're focusing on here is, if you look at this, if you put this all together, it's f inverse of f of x equals x, right? If you look at the beginning here that I put in the box and the end here that I put in the box, that's the property. So what essentially happens is that the inverses cancel each other out. You see this? F inverse, oops. Get this in yellow. F inverse, it's supposed to be in yellow. There we go. F inverse, when you compose it with f, it cancels it out and you just get then x left. That's basically what's happening. Okay, so that's one property. So when you compose when you compose an inverse function with the original function in this manner, you get back x. At number 2, let's say we go the other direction. Let's say we start with f circle f inverse of y. So in this case, I have the blue function here on the left, and I have the red function, the inverse function on the right, and I'm plugging in y. So if I wanted to write this out in detail, I'd write it as f on the outside, and then on the inside I'd put f inverse of y. Now let's follow this through. So I'm going to keep the f on the outside, and I'm going to figure out what is f inverse of y. What is f inverse of y? Well, I'm starting here with y, so y is here what I'm starting with. So y is going to get sent through the f inverse function. That's going to come out as x over here, right? So I'm going to replace f inverse of y here with x. And then we take x and we plug it into the f function. So let's take x and plug it into the f function here. And out the other side comes y. So if you pay attention to this, the beginning here and the end, we have f composed with f inverse of y equals y. That's our second property. So notice what's happening. Basically, the f and the f inverse are canceling out, and you're just getting the y. So that's the second property of composition of functions with their inverses. Basically, you get out either just x or you get out y, depending what variable you're using. If you're using the variable x, then you just get out x. If you're using the variable y, then you get out y. So if you want to test whether two functions are inverses of each other, you just compose them together in these two ways and see if you get out x and you get out y. So let me do some examples of that. So I'll do a couple of examples. Let's verify that f and g are actually inverses of each other. Inverse functions of each other using the properties of inverse functions. So number 1, I have a function f is going to be 3x plus 9, no, 7x minus 8, 7x minus 8. And g of y, I'm going to call it, g of y, so the input is a y rather than an x, interestingly enough. It's going to be y plus 8 divided by 9. No, but divided by 7, I think. I think that's a 7, yeah. So I want to verify that these two functions are inverses of one another. So I'm going to call this first one f of x. It's going to be my red function, and g of y is going to be my blue function. And what I'm going to do, I'm going to compose these in two different ways to see if we get x in one way and y in the other way. So let's start with let's start by composing f of g of y. We'll do that. F circle g of y. We'll do it like that. So I'm putting the y there because the g goes with the y. So you see the g right here is right next to the y, so I'm using y there. So you write this out. This is going to be f of, and then inside g of y. So I'm going to leave the f alone. And inside I'm going to put what g of y is. What is g of y? G of y is replacing this, y plus 8 over 7. Okay, now I'm going to take that blue, I'm going to plug that into my f function. I'm going to have 7 times a blank minus an 8. Place in my blank where my x was, I'm going to put the y plus 8 over 7. And now it's time to simplify. How do you simplify? Well, the 7 on top cancels with the 7 on bottom. So we end up with y plus 8 minus 8, and then the 8 and negative 8 cancel, and we get back y. Okay, so basically what has happened is, if you look at the beginning, it should be a y, not a g, just so you know. That is a y. What's essentially happened is this f and this g have canceled, and we've gotten out y. So that verifies one direction. Now we have to compose them in the other direction. We have to do g composed with f. Now what does f go with? So we're going to figure out, okay, f goes with, look back up here, f goes with x. So I'm going to plug in an x right there. So if I write this out carefully, it's not writing, there it goes. If I write this out carefully, I'm going to start first on the left with g, and then inside of that I'm going to put f of x. There it goes. It's not changing colors, f of x. So remember, when you're composing functions, you leave the outside function alone, and you work on the inside. So f of x here we know is 7x minus 8. So I'm going to put in red 7x minus 8. I'm going to have to plug in 7x minus 8 into my blue function. So my blue function looks like a blank plus 8 over 7. And inside of that blank, I'm going to put the red 7x minus 8. So we'll simplify this. Let's see, the minus 8 and the plus 8 cancel. So you get 7x divided by 7. And then the 7's cancel, and you simply get a x. So essentially what's happened is the g canceled with the f in this manner, and you got out x. So you have to do it both ways when you're verifying that something is an inverse function. You have to do f composed with g of y and g composed with f of x. And you get one is y and one is x. So thus, g is equal to f inverse. The g function is the inverse of f. Okay? Yeah. So we're verifying that g is in fact the inverse of f. So we can call g f inverse. I'll do one more example here. Set number 1. Let's do number 2. So I have f of x is x minus 3 squared plus 8 for x greater than or equal to 3. And let's say that g of y is the square root of y minus 8. And then outside of the radical plus 3. Calling this one red. Calling this one blue. To verify that g is the inverse of f, we have to compose them. I'm going to start with composing f composed with g of y. That means I have an f outside, and then inside I have g of y. So I'm going to replace my g of y here in the inside, right here, with the square root of y minus 8, and then plus a 3. Okay, so now I'm going to take this blue stuff and I'm going to plug it into my red function. So I have a blank minus 3 close parentheses squared plus 8. And in place of that blank, I'm going to put in place of this blank right here, I'm going to put my blue stuff, if I can squeeze that in. Can we squeeze in the blue stuff? Yeah. Square root of y minus 8 plus 3. So how does this work, this simplification process? Well, first of all, the minus 3 here and the plus 3 cancel, and you get the square root of y minus 8 in parentheses. And then you're going to square. Basically, the square here will cancel off that square root, and you'll simply have in parentheses now y minus 8. Bring down the plus 8, and then the plus 8 and the minus 8 cancel, and you just get simply y. So if you think about it, basically the f and the g canceled, and you got y. Okay, now let's compose in the other direction. Let's do g composed with f of y. So we'll start with the g first, and then inside of the g, f of the y. And that should be red, f, come on. So I'm going to leave the g alone out front. And inside of the g, I'm going to put what f of y is. It's, what is that? X minus 3 squared plus 8. Okay? And now we're going to plug in the red stuff into the g function for y. So what do we have? The square root of blank minus 8 plus 3. Right, that's the form of our g function. In place of the y where the blank is, we're going to put the x minus 3 squared plus 8. So what happens, well, we can cancel out the 8 and the minus 8, and we have the square root of x minus 3 squared, and outside plus 3. And then basically the square here, the square and the square root are going to cancel under the circumstances that have been set up for us, and we're going to have x minus 3 plus 3, and then the minus 3 and the plus 3 cancel, and we get simply x. Ooh, I made a mistake. I should have been putting in a y here back in the beginning. That should have been a y. Why should I have a y there? Come on, let's get a y there. An x there, I mean an x. Why should I have an x? Because you want to figure out what goes there. What goes there, well, you look back here and say, well, f goes with x, so that should be an x right there. I don't know why I had a y there. Yeah. Just a writing error. So yeah. So these will cancel out, right? And that's what you have. You have x there. That's the idea. So we can conclude then, since we've done these two compositions, we end up with y and x respectively. You can say that thus, g is in fact f inverse. Oh, there's one more thing I want to mention. I forgot to mention. So maybe you're wondering, what is this whole thing about right here? What is that about? So we never actually talked about what that is for. So it turns out you actually need the fact that for this red function f, you need the x values to be greater than or equal to 3. Let's think about that for a second. Let's think about the graph of this. So I have this function f of x equals x minus 3 squared plus 8, right? That's our function, our red function, is that right? Yeah. And you got this strange condition here. We never actually used it directly when we're working through this verification process. Why do we need that x is greater than or equal to 3? Well, let's graph this. This is going to be a parabola, right? It's a quadratic, so it's going to be a parabola where you have shifted right 3 and up 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to look something like this, right? The vertex is going to be at 3, 8. And it's going to open upwards. We know it's going to open upwards like this because it has a positive leading coefficient. Now the problem with this function is it's not one-to-one, right? It fails the horizontal line test. So basically what we're doing here, we're going to only look at this parabola to the right of 3. So we're going to basically look to the right of 3. So that means we're going to get rid of the parabola to the left of 3. So we're only focusing on the parabola to the right of 3. So if I can get this to right. So the vertex was at 3, 8. And we're only looking at the parabola on this side. That's what this x greater than or equal to 3 means. So we're disregarding the left side. So we're disregarding this side over here. And now notice our function is in fact